Okay, so let's finish up 4 and 5. They are more straightforward. 3 was the really tricky one here. So let S be the equation of the line from problem 3. So that was an equation of the line that went through A and was perpendicular right here. Went through K, or BE. And let P be the intersection, so there's P right there. And this asks, what is the vector dP? So what about this vector here? What is that vector? Well, we know this point is 2, 2, 0. We know the point P, which was which was 5/3, 1/3, 2/3. That was the point. I could have done those in coordinates as well. And so here we just have to do the subtraction to figure out what that is. So what's the difference between those 2 points? And we're going to subtract the tail. So we want to subtract out D. So 5/3 minus 2, 1/3 minus 2, and 2/3 minus 0. And that gives us a minus 1/3, a minus 5/3, and 2/3. Okay, that should be equal to dP. And does that make sense? As a vector, in the x direction, we move, it says we move 1/3 this back towards the origin. So from here we move, let me get a different color, back 1/3, but this is a distance of 2. So 1/3 is just going to be about there, 0.3 is 1/6 of that distance. And then in the y direction, we move back towards the origin a negative 5/3, so almost all the way there, and then we go up 2/3. So that makes sense with those coordinates. So that was all we needed to do for 4. Now 5, what about 5 says what's the direction vector of S? S is the equation of this line here. We just need one. We can just take the vector A to P. So what is A to P? There, it's a little bit bigger. What's A to P? Well, we subtract the tail, so we can do P minus A to get the vector A to P. So P minus A. P is, I'm just looking up the right, see the coordinates is 5/3, 1/3, 2/3, right? And then subtract A, which is 0, 0, 0. So 5/3, 1/3, 2/3. So that is a direction vector of S. Now, some of you could just read that off. Of course, hey, if we're going from the origin to that point, then that's a vector, and the vector in standard position is just that vector that has the coordinates of P, so that can be a direction vector. So why did I have you guys solve for these things? Because with that information of dP and AP, we can calculate the angle that I need to make the cut, to actually make this on out of wood on a table saw. So the cosine of that angle, the dot product will tell us the cosine of the angle between those. So if we take, so the cosine of theta will be a minus 1/3, a minus 5/3, and 2/3, and 5/3, 1/3, 2/3. Now it's hard to tell exactly what angle it's going to give us, whether it's going to give us like the angle on the outside or the angle on the inside. It always gives the one less than 180 degrees, but our angles are going in here, and you have to place them at place them from end to end, like tail to tail, to see what angle it's going to give you. If we changed the direction of D, so it might be easier if we had changed the direction of D. We'd have one going there, and we could think of, we could think of the angle AP vector continuing on, and then we'd know that it would be that angle we're searching for. That's if you go across like the front face, and then you just keep on going, and you want to know what angle that makes with the front of this face, that line that goes from P down to D. But our angle is going a different direction, so what it's going to give us is the angle coming around there that would go on the inside of the pyramid. So if you dot that, then you end up with a minus 5/9, a minus 5/9, 4/9, and you add those all up. I better do this better. So a minus 5/9 plus a minus 5/9 plus 4/9, and I add up all those. That's a negative 10/9 plus 4/9. So 10. So 4 minus 10 is a negative 6. So negative 6/9. That's the cosine of that angle. So theta will equal the arc cosine of a negative 6/9, or a lot of you will be more comfortable calling it inverse cosine of a minus 6/9. And that is, those are the same. And that, you pull out your calculator, punch it into Wolfram Alpha, or go just to Google. If you just say arc cosine of a minus 6/9 in degrees, because it tends to give you it in radians, then we get 131.81 degrees. And now if I cut that in half, that will tell me the angle that I need to set my table saw to if I cut the, to actually make this cut. Because I'm going to have something like this. The 131 is this angle, so I cut it in half. So it will be, so both of those are the 131.8. So half of that is 65. So just this much is 65.905 degrees. Oh, looks like a 0 degrees. So now I can actually make that on my table saw. Thanks.